Alright, take a look at the key for the exam from 2014 for chapters 4, 5, and 6. Okay, good question asking us about what these things are to each other. A little bit of a thing here for this first one. These are actually identical. So the wedges and hatches here don't matter because both there's two methyls there. So that this actually is not an asymmetric center. And neither is this. So really it doesn't matter in that case. These two are not cis-trans because this methyl are the same. You can't call this E or Z, so these are actually identical too. These are diastereomers. The OH is both wedge there, but then the other stereocenter is different, so that makes them diastereomers, different physical properties. Here, these are just constitutional isomers. There's not an asymmetric center, there's not an EZ, so there's no asymmetric center, it's not an enantiomers, diastereomers. They're not identical, so they're stuck being constitutional isomers. For this one, it's just a matter of indicating E and Z and S and R. So you got to do your rankings again, red, white, and blue. R rotates clockwise, S rotates counterclockwise. E means they're as a trans, Z means they're on the same side. This is working on this practicing your rules, ranking. This, some naming. Gotta be careful with these. Find the parent chain, find the longest chain with the alkene in it. So that's hexene. It's on the 2 carbon. Want that number to be the lowest possible. Everything else goes off of that. So 3, 4, 5 trimethyl. Then we need to say if it's E or Z. So we do our rankings, we split down the middle. Priority, so it's E. Same thing here, methyl cyclohexene, the ring, it takes priority. We want to do the numbering such that we have the one with the alkene with the lowest number and the substituent with the lowest number possible. So instead of going this way, we want to go this way, because this gives 1, substituent 1. So the lowest number possible with the first one, and so on and so forth. Again, find the longest parent chain with the alkene, go from there. Hexadiene cyclo, so 6-membered ring. Hexadiene means there's 2 alkenes, and it's on 1, 4, so 1, 2, that's where the first pi bond is. 3, 4, second pi bond, and then 3, 6, because the methyls are at. Here, we're telling you heptadiene, so it's a 7-member carbon ring, or chain, and there's 2 pi bonds, so heptadiene. And the tricky part here is 2, 4. That's where the alkenes are at, and 5, 6 is dimethyl, but you need to notice that you need to make it Z, so that the one on 2, 2, and 3 has to be Z, so it's going to be on the same side, and the one at carbon 4 has to be E, so that's a little tricky. Make sure you draw it correctly. Alright, for these ones, these are testing and reaction knowledge. Do you know about what products were formed, and what reagents are needed, and what starting materials might come from? So here's O3, doesn't touch the benzene ring, but it splits right down there. So you get a ketone and an aldehyde. H2, palladium on carbon. It adds cis, so you'd have both of these be formed. So you'd have both the H's on either side with the methyl going up, so that doesn't change. For this one, if you wanted to add an OH and an H, use H plus and water, or H2SO4 would be fine too. For this one, you don't have the reagent, so you look at this and say, well, we have an anti-Markovnikov product, and it's cis, the OH and the H are on the same side, and it's an anti-Mark product. So that means you need BH3 and OH minus, step 1 and step 2. For this one, you're adding, using HBr, and you're adding 1 bromine. So that means this came from an alkene. And 2 of the possibilities could be either the alkene here, or even the alkene here could work, or there as well. So those are possibilities where the actual starting material came from. Here, you see you have a 2 trans relationship between the oxygen, the ether part, and the chlorine. And so that should tell you that you need an alkene. And you need the alkene to have the H, this H and this methyl on the same side, and these 2 methyls on the same side, so you need an alkene that looks just like this. Another good problem here is the star which atom or lone pairs in the following compounds are electrophilic. Right? So what parts are electrophilic? If you're bonded to something that's electronegative, that makes you electrophilic, or if you don't have a full octet. So the carbon bonded to an iodine is going to be delta plus because iodine is playing with electron density. This carbon bond to a double bond to an oxygen is going to be delta plus because it's playing with electron density. Right? Electrophilic means electron deficient. The boron doesn't have a full octet, it has an empty p orbital, so that's electron deficient. As you move over, the H here is actually electron deficient, not the oxygen. Right? Just because there's a plus charge doesn't mean that's where it's electrophilic. It's actually on the H that's electrophilic. That's going to be the most delta plus spot. Now if we move down, let's say which ones are nucleophilic. Well, now people here will say, some people might say chlorine, but chlorine's on the far right of the periodic table and very electronegative. It's not going to want to give up its lone pairs. Nitrogen, on the other hand, is going to be able to do that. Same thing here, so now it's a pi bond. We've seen pi bonds as electrophiles. Here, the oxygen lone pair is more willing. Oxygen with the negative charge, again, those lone pairs are more willing to be donated. For this problem, this is more of a work on answering the question correctly. So we're telling you the products. All right, so you're being showed the products, A and B. So this is a good numbering carbons, bonds broken, bonds formed type system. So if you do the HCl, you form a carbocation. You can form a carbocation on 5 or 6. Either way, they're both secondary, so there's no real preference. So one mechanism shows plus charge being on 5, right? And the chlorine going there. That would give you actually B. That's how I drew this wrong. So actually go to get B. And this would give, if it goes to 6, it goes to A. So same difference. But then they all know the major product is. So now if you look at this carbocation B, you would notice, wait a second, I can make that secondary carbocation a tertiary one by doing a methyl shift. So I shift a methyl, it doesn't matter which one. Chlorine comes and attacks, and that actually gives me the major product because I go through a tertiary carbocation. Number your carbons, bonds broken, bonds formed. Right, drawing all your lone pairs in, all that kind of good stuff really is helpful here. Alright, for this one, it's kind of your classic, just draw the mechanism in. For this case, we want to see if you know the BR2, how that would work. Be sure to draw all intermediates, right? So I wanted you really to draw both enantiomer bromonium ions, right? Electrons attack, break the bromine bond, bromine lone pairs comes back down. Bromonium ion, one carbon is more substituted than the other, so that's where the methanol attacks, kicks off, balance our charge. They're still, right, you can come from either way, so these are two enantiomers. Show the electrons being taken there. Going up, notice how they end up being trans. These are two enantiomers of each other. So it was a stereoselective reaction, and also retroselective in this case. So here's just answering some questions about a free energy diagram. What's the energy difference between the overall kinetics? What energy determines overall kinetics? What's the rate determining step? The rate determining step is from the highest hill, A to B. What energy determines the thermodynamics, right? So fast is kinetics, right? How fast? Thermodynamics, how much? So it's between A and G. Is it exergonic or endergonic, right? It's exergonic. What is the transition state? B, D, and F. What are intermediates? C and E, right? C and E actually have fully formed bonds. B, D, and F do not. Those transition states, that's where the arrows are. As we show when we draw a mechanism. And the things in between time, like things like carbocations, things like that, are the intermediates. Good one. Here about the 3 factors that affect the rate of reaction. Hint, ice fishing, of course. Concentration matters, a number of things. The energy, the movement of the molecules, and then the proper orientation of the collisions, of course. Right, so lots of fish moving fast, but also hitting our hooks in the correct orientation. Here, pi bond attacks, HBr, good numbering system. Form a secondary carbocation, which is good. We can do a hydride shift though and get a tertiary carbocation that attacks. See if we can draw intermediates for this reaction for number 11. Alright, so A and B are intermediates. Every arrow is a hill. So we have 1, 2, 3 hills. A is higher energy than B because it's secondary versus a tertiary carbocation. I'm not really worried about C or the starting materials and products where they add energy to each other. A little bonus question. Having a pi bond attack. Right, we could form a carbocation in either place, but it's better to form a carbocation here actually because we have lone pair resonance. We have a full octet, so a lone pair can come down, but create a full octet, and then the bromine can come and attack. We lose we have the bromine head there, and everybody knows there's no charges left. Of course, the meso compound is a internal mirror plane.